Good evening. Please welcome Thomas Kleffel and Christian Daniel. The guys that brought you OpenTOM will do this talk about DVB-T and how it works. Please welcome Thomas Kleffel.
Hello, everybody. Well, after TomTom, we had to do something new, and this year it's going to be our own DVB-T transmitter. So, well, we give you something to hack upon. Afterwards, well, this time we created something, and that's something somebody else can crack, nothing like the last year. The presentation or the lecture has 6 major topics. The first step is audio and video encoding. Then we will show you how the DVB packetizing works and what parts belong to a DVB stream. After that, Thomas will take over and explain the channel encoding and the modulation, which is the major part of our work. And after that, you will see, well, the realization, the hardware, which does the job. And finally, we will show you the Congress DVB-T transmitter setup, which is in place and working right now. Well, the picture is not perfect, but, well, this is one of the few places, this room is one of the few places where the reception is not really good. Well, despite of the hacking center downstairs. Well, the signal path overview is here. It shows the stations, the TV signal has to pass from the camera to the watcher's TV set. The first step, obviously, is the camera. The next step is the MPEG-2 encoder. We're using a hardware for that, well, which is not built by us. You can buy that for cheap. The next step is the multiplexer, which has to do, which has to combine all the streams coming in from the different encoders and make them form a DVB stream composed of several programs. So the idea behind DVB is better using of the channel bandwidth compared to the old analog TV system. And this is done by using the same bandwidth, frequency bandwidth, and putting more streams into that one channel. For that we need a multiplexer, and after that several additional data streams are inserted. It's the program service information tables, which tell the receiver what programs are in that stream and, well, what the names are and who is broadcasting them and what needs to be done to receive them. After that, our work comes, the modulator. The modulator has the job to transform the bit stream into the radio frequency signal by breaking the packets up into bytes, and after that, well, adding error correction and then breaking it up into single bits and modulating them on the carrier signal. After that, the antenna comes, and that's where our responsibility ends. Receivers are cheap, and it doesn't make any sense to build them. Well, it makes sense, obviously, but not for us, since chips are really, really cheap, made by Chinese companies, so, well, no need to hack here. Well, the first step here is the demodulator, then the demultiplexer, and the demultiplexer also feeds the program service information table interpreter, which helps finding the programs, and the final step is the MPEG-2 video decoder, which does the decoding of the video and audio signals in the stream, and then, well, the TV set, which the watcher uses to, well, convert back to analog signal. So, how does audio and video encoding work? This is this principal layout of the MPEG-2 video encoder. It's a predictive encoder, opposite the MPEG-1 encoder. The basic idea is that the receiver tries to guess the next picture based on information it already has. So, well, you only transmit the difference to that prediction. Everybody got that? Well, okay. Do it step by step. First, well, do you see the point? Yeah, works. Okay. Let's ignore this one. First step is to convert the picture into frequency components. What that really means, I'll show you on the next slide. Just accept that for once. Then data is reduced, which means an algorithm decides what data is not needed because we cannot recognize it. It's in the data, but we don't really see it or recognize it as information, and we don't experience a picture degradation by throwing away this data. Then after that, variable length encoding comes. This is something like PK-ZIP or something. Well, the algorithm is different, but it's what it does basically. And after that, the remaining data is packed into single packets. So what is the loop down there? It's everything in there what a receiver needs. So the quantization is reversed, then the picture is retransformed into picture data, and the motion compensator does one thing. It tries to detect movements in the picture. So you don't retransmit an area, but tell the receiver, well, there is a ball rolling, just copy the data from one edge of the picture to another, and don't retransmit the data itself. So this is done here. And after that, we have the prediction. So the encoder knows or needs to know what the receiver will predict. And after that, well, that's the first thing to do. We subtract the prediction from the actual picture that came in. For the first picture, we don't have a prediction, of course, so we subtract nothing, or zeros. And after that, we can count on the prediction and only transmit the changed data, which is most of the time not much. Well, you see me here talking, which means, well, my mouth moves, and we only need to update a small area of the picture. So the difference to the previous picture is really small. That's what the video encoding does. Okay, next to the audio encoding. Oh, slowly. This is what I promised to explain. It's the transformation into frequency components. On the left, we have the original pixel data coming in from the analog digital converter, and the block besides that shows the transformed data. So you see, this is some kind of gradient, and the transformed data mostly is 0. So the frequency components of this signal are really small, or, well, they're not small, but few, and you can compress this much better than this. This picture here has much more high-frequency components because it changes every pixel much more compared to the previous pixel. And the result is, well, it has more data in every frequency component, but still you can see how easy this would be to compress. So the idea is to transform the picture into the frequency domain and then do more efficient compression afterwards. Another thing that MPEG-2 video does is the predictive coding, which I told you earlier, it works in two directions. The stream is divided into groups of pictures. A group of pictures contains, well, an arbitrary number of pictures named, well, 10 or 12 pictures, half a second. And it starts with an iframe. The iframe is an intra-frame, and this frame doesn't use any data from any previous frame. So this is the first frame in a group of pictures with using the 0 picture as prediction. Yeah? Then we have several bidirectionally predictive frames. These use data from earlier frames and from later frames, which also tells us MPEG-2 doesn't transmit pictures in the order we are watching them. So every picture has a timestamp, which tells the decoder when to display this picture. And, well, this order is different than the order the pictures are transmitted. Well, and the P frames, they're easier than the B frames. The P frames only use previous data as prediction. So, well, it's quite complicated. Most of us don't want to do this at home alone by coding that, well, using the standard as documentation. There's quite a funny thing. The standards only define how the data stream is decompressed. So how to compress it is your job to do. You can find an algorithm that works, or you can, well, you can just encode interframes and don't do any prediction, but that blows the bandwidth usage. So, well, you better use all the standard features and write a lot of nasty code. Okay, audio coding. Audio is a bit easier to understand because it doesn't use any prediction. First step is the audio signal is divided into 32 subbands. That's a filter bank doing. And the subbands are coded independently. Alongside of the 32 subbands, 512 bands are analyzed. So you do 32 subbands for transmission and 512 subbands for analyzing the data or the signal. And then you decide what subbands need how much bandwidth to represent the original signal as much or as accurately as possible. Here the black magic box is the psychoacoustic model, which is much improved in MPEG-3. Well, MP3, you know it all. And, well, MP3 adds the prediction as well, like the video encoding. The quantization uses the information from the subbands and the analyzing results from the 512 bands to decide how to distribute the available bandwidth, and then afterwards the remaining data is just encoded into packets. Here in the voice prints, you can see what happens to the audio data when encoding is really rough. We have here an uncompressed audio data. This is the time axis. This is the frequency axis. And the the hue value of the pixels shows the intensity of this frequency. So we have here near silence and some, well, sounds in here. And after decoding, it's it's gained a lot of distortion. So 96 kilobits is a bit small for this kind of signal. We also see that we have a cutoff frequency here. The codec just throws away higher frequencies. Yeah, any questions to the encoding? Okay, then